everybody, better late than not at all. So I'm coming to this week motivating videos or guiding videos, whatever it is. We shall be dealing with the linear mappings. And as I was alluding to earlier, if you deal with some objects in mathematics, you always are most interested in mappings between the objects which preserve the structures you are interested in. In our case, it's the linear structure. So if we deal with two vector spaces, say V and W, so these are some sets of vectors with some properties. We can add the vectors, we can rescale the vectors, we can make linear combinations. And a mapping, say phi from V to W, will be called a linear mapping if it preserves the linear combinations. So in words, well, here I call it F, not phi. So we request that the addition of the vector goes to the addition of the values. And if we resize the vector by scalar multiple of A, then the same scalar appears here. So that altogether means that if I just have a linear combination, say A1, U1 plus and so on, AN, UN of n vectors. Well, n is not necessarily the dimension. Well, don't talk about dimension. The vector spaces might be infinite dimensional, so we don't care about the dimension now. And this will be sent by the phi to A1 phi U1 plus etc. AN phi UN. That's it. And of course, this works for every field of scalars. And in particular, we can imagine what we know already, and that's the multiplication of a column of coordinates, x, so a point in Kn, by a matrix. And of course, we know already that this happens to be linear in the sense we have just requested. But because we are now dealing with abstract vectors and abstract mappings, all the properties which seem to be obvious when dealing with the coordinates, like here, via the matrices, so everything what's in the next proposition seems to be obvious. But we have to prove it because we want to deal with a mathematical theory. So we have the axioms, that's the two axioms in the definition, and we want to see the consequences. And the consequences are here. And then when you go through, you will see that actually the linear mappings behave the way one would expect, nearly. So for example, if you have two such mappings, you can compose them, right? So that's nothing but you have another psi here, and here will be something like what U. And of course, you first map the vector by phi, then by psi. And this must be linear, because if you do it here, what would happen is you simply apply the psi, and it would then be A1 psi of the phi U1, which is phi psi U1 at plus etc. Right? So obviously this would be again linear, right? So the composition from here down to here would be again linear. Well, there is a nice concept of the kernel, because we can request to know all the vectors in V which will be mapped to 0, right? And in general, it's clear that each pre-image of a vector subspace will be again a vector subspace. And 0 is the smallest possible subspace, so kernel of F will be a nice subspace of the vector space V, and that's called kernel. Similarly, image of F not necessarily is the whole of W, but it's always a vector subspace. What's interesting is that if we go to sums of vector subspaces, which we discussed last week, then of course it's obvious that the image must be a vector subspace, and the smallest vector subspace is the right one, and that's the sum of the two images. But for the intersection, it's more complicated. Imagine we would have, say, a mapping which would be working on R2 to R2. And say that I send E1 to E1 and E2 will be also set to E1. So the image indicated by the dashes will be simply twice the same E1. Then the intersection of the images is just the whole line generated by the E1, whereas the intersection of the two subspaces which are generated by E1 and E2 is just 0. So you see that the inequality is really strict here. Right. What's proved here also is that if you have an isomorphism which is linear, then the inverse is also linear. That's also a simple observation. So that's here. And now we come back to the coordinates again. So let's see how it works. So if we go to the coordinates again, so we are here. So we have got the, well, first of all, let's notice that the coordinates of a vector in a basis itself are actually a linear mapping, right? That's absolutely obvious because if you take a vector u, so let's go for the better marker, u equals, say, x1 e1 plus xn en, now n is the dimension and e1 through en is the basis, then this is mapped to x1 xn transposed, right? So a column, so I wrote it as a line. And this is obviously linear because if I add two such u's, so the coordinates add, right? And if I multiply by a scalar, I get the coordinates multiplied. So this is exactly what we wanted from a linear map. So every choice of a base is actually a choice of a linear isomorphism of the vector space with k to n, if it's a finite dimensional space with a base, right? And this is a particular linear isomorphism. So in particular, we see that all the vector spaces are up to isomorphism, the same as our kn's. Except if we restrict our attention to kn with one fixed base, then mostly we have a wrong one to understand our objects, right? And therefore we want to see how these things work in abstract way. And if I do the same on the image with another base there, then of course I see that the coordinates can be pushed up by the isomorphism given by the base, the inverse one, then mapped by f, and then thrown down. And what results is a linear map from kn to km. And moreover, we know, easily we see, so that's this one, we easily see that the downstairs dotted arrow is actually a linear map given by multiplication by a matrix. And the matrix is seen from here, right? So if we take u1 through un, will be the basis u underlined, and I map it and express the values as linear combination on the other side as the basis, right? So you see, this will mean that I would here take the coordinates which have got 1 at the first position and 0 everywhere else, and what I get here is the first column in a matrix multiplied by this, right? You copy the first column and you write it as coordinates in the basis V. And you do the same with all the elements in the base. So in general, you simply write the values fu1, fun into a matrix, right? So this will be just columns like this. this will be the last column like this. So I will have as many columns as the number of the base elements in the first space, and the columns will have as many rows as the number of the elements in the other base. So it will be n here and m here, right? And so summarizing, it's most simple. So whenever you want to see a mapping in the abstract value, it's actually a multiplication by matrix, and this happens in each choice of the bases in the beginning and the end, right? And that's how it is. Let's go further. So in particular, if we choose the same vector space and the identity mapping, which means I don't change the vectors at all by mapping them to themselves, and then I choose two different bases, then you see immediately that the identity mapping will be expressed via a matrix multiplication, and this is the change of the bases. So that's the coordinate transition matrix, and it allows us to transfer the coordinates from the first copy of Kn corresponding to the base u to the second copy of Kn corresponding to the base v, right? And here it is how we know how to do it, right? So we simply write the old bases in terms of the new bases, and this is how it works, right? So the new ones will then get expressed by the matrix multiplication. And of course, by the very definition, if you want to go the other direction, then you must get the inverse matrix. And we know how to deal with inverse matrices, how to compute them, and the Sage will do this for you anyhow. Moreover, this simple point of view allows us to understand how the composition of the linear mappings works. Because if I have two such mappings, I can write them in such a scheme. And I choose now three bases on the three different vector spaces. And for each of them, I get the matrices expressing the mappings as the matrix multiplication. And clearly I can go over the diagrams so in such a way that I go up, right, down, up, right, down. And going down and up here makes nothing because it's V and V inverse, right? So this shows that actually the composition upstairs corresponds to the composition downstairs. But the composition downstairs is achieved by the matrix multiplication. I simply go from X and multiply the X by A. That's the matrix of F in the chosen basis. And then I multiply the result by B in the other couple of chosen bases. And matrix multiplication is associative, so it doesn't matter how I make the brackets, so I can make the brackets this way. And this tells me that the composition of linear maps corresponds to the composition, well, to the multiplication of matrices here in the given choices of bases. Right. So the last thing I want to tell in this short video is to talk about linear forms. So linear forms are the simplest linear mappings, right? So it's linear mappings which eat a vector and produce the scalar from the field the vector space is over, right? So the matrix of linear forms will have one line and so many columns as the dimension of the spaces. So instead of columns of vectors, here it will be lines of vectors. And of course the linear forms, as well as all the linear maps and the matrices themselves, form also a vector space because we can add them. We can multiply them by scalars, right? So that all works. And in particular with the linear forms, there is a special choice of them. If I start with the basis, say if I start with the basis E, underline will be E1 through En, then I can write down the bases which I will denote as E star, and it will be E1 star through En star, called dual bases. And the definition of the dual basis is that Ei star evaluated at Ej equals 1 if I equals j and 0 otherwise. Right, so you see that's actually the dual basis is exactly what you get if you view the coordinate choice. So the basis gives you a linear map from the vector space to coordinates. And if I consider each of the coordinates separately, so I want to read only what is the i's coordinate, then this is exactly the i's linear form from the dual base. And you see immediately that the dual space, so all the linear forms are generated by these linear forms, and therefore for finite dimensional vector spaces every space has got its dual space V star of the linear forms on V, and the two spaces are isomorphic. They've got the same dimension. And all the spaces, vector spaces with the same finite dimension, are isomorphic because you choose bases in both of them. You take the linear isomorphism given by them there and back with the other one, and that's the linear isomorphism which connects the two spaces. Right. So that's it. That's it for this video.